warm welcome to all of you in this second session on machining. Before we initiate our discussion on this particular aspect of machining, we will just like to review what we have discussed in the previous lecture that was titled as Machining Fundamentals. In Machining Fundamentals, we saw that what is the basic operation of machining, that we defined as a material removal process. Then what are the various types of processes that are covered under the machining operation. Thereby we discussed that it can be a cutting process, the cutting by a single point cutting tool or a multi-point cutting tool. On the basis of single point or multi-point cutting tool, the cutting processes can further be classified. Then we said that there can be abrasive processes also, for example grinding, and there can be non-traditional machining operations also which use electrical energy or the energy of the lasers or chemical energy. So, depending upon the requirement, we have to choose a machining operation. Then we saw what is the necessity of the machining operation. So, in necessity we saw that if dimensional control is very stringent or dimensional stability has to be a certain or the tolerance levels are very stringent, then we have to go for a machining operation. We also saw that if the volume of production is not too large, then we can go for a machining operation. So, we tried to establish machining as an important manufacturing process for converting a raw material into a final product which undergoes various processes. In the light of our discussion, we also discussed that how machining compares with the near net or net shape manufacturing technologies. We concluded last lecture with the limitations of the machining operation, that what are the particular limitation areas, whereby we concluded that the material is wasted in case of a machining operation in the form of chips, or the material is removed in the form of chips which are later discarded. Another limitation of the machining that was noted was that the volume of material may take longer than shaping by other processes. So, whatever volume we have to remove, it may take longer as compared to the other manufacturing processes. So, we noted that with the help of example, if we take a case of a rod and we want to reduce the diameter of that rod, then there are number of operations that can be performed to accomplish this objective. So, we have seen that if we go for a machining operation, it may take a longer time as compared to other conventional metal forming or metal working operations. Then another limitation that was noted was that if we are not able to perform the operation or the machining operation properly, the surface finish that we will get will not be according to the desired specifications or according to the desired quality levels. So, we have seen that machining has certain limitations. What is the necessity of machining, that we have discussed in the last class. Just to take a thread from wherever we left in the last lecture, we have just seen that we concluded there with the help of limitations. That is what we have started our lecture today with, the limitations of machining. Now, an important aspect of machining is the machinability. There are numbers of types or there are varieties of materials that are available with us. There may be some materials which are very easily machinable. There may be other materials which may be very difficult to machine. So, how do we rate a material, that whether we will be able to machine it or we may not be able to machine it? So, the basic aspect or the basic mark or the basic gauge is the machinability level, or the machinability. It can be in the form of a number also. The machinability can be on a scale of 0 to 100. Now, depending upon whether it is easily machinable or it is difficult to machine, any number will be got. So, the machinability aspects need to be studied in detail. So, the machinability of a material is usually defined in terms of 4 factors. Now, what are these 4 factors? These 4 factors are the surface finish and integrity of the machined part. The surface finish and integrity is the first important point that has to be taken care of while we suggest or while we comply or while we say that this material is easily machinable. So, this is the first aspect that has to be taken care of, that is the surface finish and integrity of the machined part. Second important aspect that has to be ascertained is the tool life that is obtained. Now, in the previous lecture we have seen that machining operation can be considered as a system, and there are three important elements of the system. What were those three important elements of the system? Those three important elements of the system were the workpiece material, the tool material, as well as the machine or the machine tool. Now, if we want to say that a particular material is machinable, we need to study the tool life that has been obtained while machining that particular workpiece. The third important point to be taken care of is the force and power requirements. Now, we take example, suppose there is a material for which the forces required is much more, or the power requirement is extremely high. There may be other material for which the power requirement may be less. So, depending upon the force and the power requirement, we may somehow say that this particular material is easily machinable, this particular material is difficult to machine. Then the fourth important point is the chip control, that how we are controlling the chips that are getting formed. It is easier said than done. It is very difficult to classify the materials on the basis of their machinability, because we have to carry out a multi-objective optimization here, because there are number of objectives. For example, we take an example, we compare two different classes of materials on basis of their machinability. Now, these two classes of materials are entirely different if we consider their mechanical as well as their physical and chemical properties. Now, these two materials are, first one is, suppose we take an example of steel, and the second material that we are considering is a polymer matrix composite, which falls under the category of advanced materials. Now, we want to compare the machinability of these two materials. Now, there are four factors that have to be considered. Let us consider factor number 1, that is surface finish and integrity of the machined part. Now, surface finish that we will get while machining steel will be very good, or the surface roughness will be less and the surface characteristics will be very good. Whereas, if we machine a composite material, the surface finish may not be that good. The surface finish needs further finishing operations, or we need to treat the surface for further or subsequent operations. So, surface finish is comparatively not good in case of composite material, it is very good in case of steel. Now, the second part, suppose we are machining it using a standard high speed steel tool. So, in case of isotropic material, or in case of a material that we have chosen, suppose we take a simple grade of steel, the tool life that is obtained with high speed steel or a carbide tool will be good. Whereas, in case of a composite material, the tool life that we are going to get will be less. The third important point that we are going to consider is the force and power requirement. So, the power requirement in case of a machining of a steel or machining of any grade of steel will be very high, whereas the power requirement in machining of a composite or a polymer matrix composite material will be extremely less. Now, depending upon the exact composition of the steel that we are using, the chip control, sometimes the chips may form in a continuous manner, or the continuous chips may be formed, whereas in case of a polymer matrix composite, the chip disposal is not a problem, because the chips will be formed in the form of a powder, or very small discontinuous chips will be formed, blockier chips will be formed. Now, we have seen that out of these four parameters that are used to ascertain the machinability of a material, there is a material which is very good considering the first two parameters, that is the surface finish and integrity is very good, and the tool life that is obtained is also very good. But there is another material which is good in force and power requirements, because the force required is less, the power requirement is less. Moreover, the chip control is also better. Now, how we can classify, how we can say that the machinability for this particular material is good and machinability for this particular material is poor. So it depends, then we have to optimize depending upon all these parameters, and we have to see what is our objective function, and depending upon that objective function we can finally classify, or we can finally same grade of materials or same classification of materials, we can grade them on a scale from 0 to 100, and then we can say that this is machinable or more machinable as compared to this material, or this is less machinable as compared to this material. So more and less on the basis of where the material falls on the scale of 0 to 100 can be done. But if the materials are substantially different, then the scales definitely will vary. So it is not that easy that we can very easily say this is easily machinable or this is difficult to machine. It depends on a number of parameters that we have seen here. 4 parameters have been identified, that is, the first one is the surface finish and integrity of the machined part, tool life obtained, force and power requirement, and the chip control. Now if we say, let us forget about the scale on which we are going to classify or which we are going to rate the different materials according to their machinability. Now we are not going to go into that intricacy or that detail, but let us consider what is good machinability. Now good machinability indicates good surface finish and integrity. So the surface finish should be good and the integrity should also be good. Then long tool life. So the tool life should be long, maybe certain particular hours of operations, and low force and power requirement. So if any material, if the power requirement or the force requirement is less, the tool life for machining that particular component or that particular material is long, and it indicates and the machining operation results in a very good surface finish, then we can very easily conclude that this material is easily machinable or it has very good machinability. Also in manufacturing plants, I have said that it is different factors are there and it is very difficult to optimize on all these factors simultaneously. So in manufacturing plants, tool life and surface roughness are considered as the most important factors in machinability. So we have seen, although there are 4 factors that have to be considered for ascertaining the machinability of a particular material, but there are 2 factors which are considerably important as compared to the other 2 factors. So what are these 2 factors which are more important? Those are the tool life and the surface roughness. Now for example, we take a material, we machine it, and the resulting tool life for machining that particular material is considerably large. Moreover, the surface finish that we are getting on our workpiece is also according to the desired level or also according to the specifications and the requirements, then we can say that this particular material is machinable and its machinability is good, because we are getting a very good surface finish and the tool life is also considerably long. On the contrary, if we take an example of a material for which, suppose we want to drill a hole, even after drilling 5 holes the tool abrades, we are not able to make further holes using the same tool. So the tool life is only 5 holes. So we can very easily say that the tool life is very less in this particular case. So the machinability of this particular material is not that good, and this tool wear will also have an influence on the surface finish that we will get. So in order to conclude on this manufacturability aspect, there are 4 important points that have to be taken care of while ascertaining the machinability of a particular material, but there are 2 more important points. Those 2 more important points are the surface finish as well as the tool life. Now we come on to the formation of chips. So basically machining is a material removal process, In material removal process, some of the material will be removed from the surface and that will result in the formation of the chips. Now, a number of interrelated factors affect the metal cutting. The more important are, although there are a number of factors that will affect the metal cutting operation, but there are certain important parameters or certain important factors that influence this. So, what are those? That is the properties of the work material. Already we know that if we are machining aluminum, which has fair degree of ductility, it will behave in a different manner, whereas if we are machining a ceramic material, it will behave in a different manner. So, there are number of interrelated factors that will affect the metal cutting. So, the properties of the work material is one of the important factors that has to be considered while we are doing any study on the machining aspects. Then the properties and geometry of the cutting tool. Already till now we have discussed that the cutting tool is made up of different materials. So, there are different materials that are used as the cutting tools. For example, we can use diamond as a cutting tool, we can use high speed steel as a cutting tool, we can use CBN as a cutting tool, we can use solid carbide as a cutting tool. So, different types of materials are there for the cutting tool. Similarly, there are different types of geometries also. For example, in turning operation, we may use a single point cutting tool. For example, in a drilling operation, we may use a twist drill. In case of a milling operation, we may use different types of milling cutters. So, the geometry of the cutting tool as well as the material of the cutting tool is also an important factor. Then the interaction between the work and the tool during the metal cutting. So, the tool is going to be in direct contact of the workpiece when we are talking about the conventional machining operations. If we go beyond this discussion and we talk regarding the unconventional machining operations, some of the operations the tool may not be in direct contact with the workpiece, but this discussion is focusing the attention on a conventional machining operation where the tool is in direct contact with the workpiece. So, when the tool is in direct contact with the workpiece, the interaction between the two has to be studied in detail. So, we have seen that the properties of the work material is the most important factor, then the properties and geometry of the cutting tool is another important parameter, and the interaction between the tool and the workpiece is the third important parameter. Now, chip formation basically is a mechanism of localized shear deformation. So, deformation is taking place here also and it is a localized shear deformation. So, chip formation basically is a mechanism of localized shear deformation resulting in the failure of the work material immediately ahead of the cutting edge of the tool. So, suppose this is the material that we want to machine, this is suppose the cutting tool. So, a localized area just ahead of the cutting tool. So, this is the cutting tool, the area that is just ahead of the cutting tool will fail and will be removed in the form of chips. So, just to summarize, chip formation basically is a mechanism of localized shear deformation. Why this material will be removed? Because of the localized shear deformation resulting in the failure of the work material immediately ahead of the cutting edge of the tool. Now, the relative motion between the tool and the workpiece compresses the work material near the tool and induces shear type deformation within it. So, there is a relative motion between the tool and the workpiece. Now, depending upon the different types of machining operations, sometimes the tool may be moving and the workpiece may be stationary. In another machining operation, the tool may be stationary and the workpiece may be moving. So, depending upon the operation, but the important point to note is the relative motion between the tool and the workpiece. Always the tool and the workpiece will be in motion, one may be stationary, other may be moving, but there will always be a relative motion. So, the relative motion between the tool and the workpiece compresses the work material near the tool and induces shear type deformation within it. So shear type of deformation will be induced in the workpiece material. During cutting, shear and compression stress levels exist within the material ahead of the tool sufficient to cause plastic strain throughout the shear zone and to exceed the material strength locally. So why, suppose the stresses are getting developed, alright, there are stresses that are being developed just ahead of the tool tip, but why the material is getting removed? The material is getting removed because of this particular point, because sufficient to cause plastic strain throughout the shear zone and to exceed the material strength locally. So material also has its own strength. So locally in that particular zone, the plastic strain that is being caused will exceed the material strength locally near the cutting edge. Such stresses is associated with extreme pressure and with forces which can be large, acting on the workpiece and the tool. So the major point to study here or to discuss here is the generation of the forces that act on the tool as well as on the workpiece. So just we can see the last 2-3 points here. Such stress is associated with extreme pressure and with forces. So extreme pressure will be developed and forces will be developed which can be large. So these will be large in magnitude, acting on the workpiece and the tool. So these forces will act on the workpiece as well as on the tool. So important point to note here is that initially we have seen, if we are not performing the function or the machining operation properly, there are bound to be certain problem areas, and out of which one was that we are not going to get the adequate surface finish for which we are going or which we are aiming at. Now if these forces and the pressures that are generated because of this particular phenomenon or this particular mechanism that is happening, then it will have certain adverse effect on the component dimensional accuracy or the component surface finish that we are producing. So here we see that forces and pressures are generated and we have to control these forces and pressures. So important point is that when we are holding a tool in a tool holder, we need to clamp it properly so that this particular tool should not fly away or this particular tool should not break. So these forces and pressure that are generated should be controlled. The action involved in the chip formation also causes distortion in the workpiece. Now the workpiece may also get distorted and the machined surface is not smooth. Already I have told the smooth surface finish may not be achieved, but torn and fragmented. The surface will be torn and fragmented. These effects can be harmful and can adversely affect the service performance until eliminated. Now what are the problem areas? These problem areas are that the action involved in the chip formation also causes distortion in the workpiece. So one important problem area is the distortion in the workpiece, and the machined surface is not smooth, the surface finish is not good. So these effects may be harmful and may affect the in-service performance of the product that has been machined. So the surface finish is not good. If we are going to assemble one particular rod or one particular shaft which has been machined and we are going to assemble it into another particular hole, so if the surface finish is not good, the fit may not be proper, and during the service operation this may come out and we may not be able to assess the loss that may take place because of this particular joint failure. So we have to ascertain that the quality that we are producing should be according to our desired level. So important point to note here is that the surface finish that we are getting should be good and there should be no distortion in the workpiece. If the workpiece will distort, the surface finish will automatically get affected. Moreover, the tool wear will also be excessive. So when the tool wear will be more, that will be seen on the surface finish of the workpiece. If the tool wears out very fast, then the tool edge becomes blunt, and when it is rubbing against the workpiece, the surface finish that we will get will be very poor. Now another important point to note in case of chip formation is the considerable heat that is generated in the cutting zone. So, we have seen that forces and pressures are generated, there is distortion to the workpiece that may result, it may affect the surface finish of the workpiece, it may also result in the excessive tool wear. Similarly, there is a large amount of heat that is generated. Now, considerable heat is generated in the cutting zone. The heat generation results in elevated temperatures. Now, when the tool is in continuous contact with the workpiece, then because of the friction or because of the rubbing, some heat will be generated. So, heat generation results in the elevated temperatures in the cutting zone, especially in the chips and the cutting tool, which is in direct contact with the workpiece during machining. Now, the tool, as we have already seen, is in direct contact with the workpiece. Now, there is a study, or there has been number of studies which have shown that what is the distribution of this particular heat, that how much heat will be carried away by the chips, how much heat will go into the workpiece, how much heat will go into the tool. But the important point to note is that while machining, the temperature is definitely going to increase, and at an elevated temperature we have to study the behavior of the tool, the behavior of the workpiece, and we have to see that when the chips are getting removed, they should be removed properly, because of the high temperature of the chips some kind of accident or some kind of health hazard may result, or some kind of accident may take place. Now, types of chips. The types of chips produced significantly influence the surface finish of the workpiece. Now, previous lecture also we have seen, now also we have seen in the limitations also of the machining operation, that the type of chip has certain bearing on the surface finish of the final product that we will get. So, how is that influencing? That is influencing when the chips that are formed are continuous in nature. So, when they are when the chips are in continuous nature, then these chips, when they are forming, may entangle with the tool holder, they may get entangled with the workpiece, or they may even get entangled with the waste disposal system, and thereby they may influence the surface finish, or they may deteriorate the surface finish of the workpiece that we are intending to achieve. So, the types of chips produced significantly influence the surface finish of the workpiece and the overall cutting operation. So, how they influence the overall cutting operation? They may influence the tool life, they may influence the vibration and chatter. So, it is important therefore to understand the different types of chips that are produced. So, there are different types of chips that are produced, that we will see in the subsequent slides, that these may be continuous in nature, these may be the chips with the built up edge, then these may be discontinuous chips, or these may be segmented or serrated chips. So, there are different types of chips that are produced, and this formation depends upon a number of parameters. Now, these parameters or the factors that influence the type of chip that will be found while machining a particular material depends upon a number of parameters. So, these parameters are the type of the workpiece, or the material of the workpiece, the operating variables. The operating variables may be in terms of the cutting speed, the feed rate, or the depth of cut. Then it is also influenced by the cutting conditions, whether we are using a cutting fluid or we are performing a operation without the use of any cutting fluid. So, there are number of parameters on the basis of which the formation or the different types of chip formation will depend. Now, already we have discussed what are the different types of chips. Just I will briefly summarize. The different types of chips that are formed are continuous chips, chips with built up edge, serrated or segmented chips, and discontinuous chips. So, now we will discuss each one of these types, under what conditions these types of chips are formed, and what is the influence on the surface finish, etc. Now, first type of chips that we are going to consider in case of machining operation are the continuous chips. So, continuous chips are formed under specific set of conditions. So, what are these specific set of conditions? These specific set of conditions are with ductile material. If the material that we are machining using a standard tool is a ductile material, then there are every chances that we are going to get continuous chips. Moreover, if the operation is being performed at relatively higher cutting speeds, then there are chances that continuous chips will be formed. Moreover, if the rack angles are also higher. So, till now we have not discussed what is a rack angle, that will be discussed when we discuss the geometry of a single point cutting tool. But here we can only try to understand that if the rack angle is higher, we are going to get the continuous chips. So, there are three conditions that have been mentioned. So, we can for ourselves see that these are again taking into account those three elements that we have discussed in the start of our series of lectures on machining. Those three elements were the workpiece material, the tool, as well as the machine tool. So, the machine tool comes into picture when we talk about the high cutting speed, the material comes into picture when we talk about the ductile material, and the tool comes into picture when we talk about the rack angles. So, continuous chips will be formed under these three important conditions with ductile materials at higher cutting speeds and at higher rack angles. Now, continuous chips generally produce good surface finish. So, surface finish that we will get if we are going to produce or if we are going to get continuous chips will be good. So, generally produce good surface finish. Continuous chips are not always desirable. Although when the material is getting removed continuously and we are going to get continuous chips, the surface finish will be good, but particularly in certain cases the continuous chips are not desirable, particularly in the computer controlled machine tools widely used today. Why these particular type of chips we do not want to get, or we do not want to get that these type of chips are formed, we do not desire that these type of chips are formed, because they tend to become entangled around the tool holder, the fixturing, the workpiece and the chip disposal system. Now, these are all the parts of the machine tool, or the workpiece also has been considered here, but the tool holder, we can see the tool holder, the fixturing and the chip disposal system, all these are parts of the machine tool, and we are considering the workpiece also. Now, these continuous chips that are forming as a result of the machining operation have the tendency to get tangled around all these four different points of the machine that have been considered here. Now, they may get entangled around the tool holder, they may get entangled around the work holding fixtures, or they may get entangled around the workpiece itself, or they may get entangled around the chip disposal system. So, this entangling, once it happens, has to be removed, then the process has to be intermittently stopped in between, and after stopping the process we have to remove these entangled chips that have got entangled or that have got like fixed with the tool holder, or they have got fixed with the workpiece material. Moreover, when they are in contact with the workpiece material, there are chances that they may abrade the surface of the workpiece and thus affecting its final surface finish. So, although while machining we get a very good surface finish with continuous chips, but if they get entangled with the different parts of the machine, then it is not particularly desirable. Moreover, these may also affect the surface finish of the final product. Now, the second important category is the built up edge chips. Now, first of all we will try to understand what is this built up edge. A built up edge, or we will call it as BUE, consisting of layers of material from the workpiece that are gradually deposited on the tool. So, till now we have read that there will be layers of material from the workpiece. So, whatever material we are removing or whatever is our workpiece, some of the part of it very small in size will get deposited. Gradually it will happen, gradually it will get deposited on the tool. So, this may form at the tip of the tool during the cutting operation. So, first point says that some material of the workpiece may get deposited on the tool or the tip of the tool gradually. So, it is called the built up edge. As it becomes larger, the built up edge becomes unstable and eventually breaks up. So, what we have seen till now, some material of the workpiece will get deposited layer wise on the tip of the tool and it will grow eventually, and after some time it will become unstable and it will part off. Now, some part of the built up edge material is carried away by the tool side of the chip. Now, tool side of the chip means that if this is the face of the tool and this is the chip that is flowing or going on to the rack face of the tool, then this side of the face is the tool side of the face and the other side is free to the atmosphere or free to the ambient conditions. So, this tool side of the face will carry some part or some material of this built up edge, and the rest of the material that is left around will be randomly spotted or randomly distributed over the workpiece surface. So, basically what we have seen in case of the built up chips, that the built up edge is formed on the tip of the tool with the material that is coming from the workpiece. So, some of the workpiece material will get deposited on the tip of the tool to form a built up edge, and it will be a gradual process and the material will be developed layer wise. It will grow up to a certain level, then it will become unstable and later on it will break up. So, when it breaks up, some part of the built up edge will be taken by the tool face of the chip and some part will be deposited randomly on the work surface. Now, the process of built up edge formation and conditions. So, this tool side of the face will carry some part or some material of this built up edge, and the rest of the material that is left around will be randomly spotted or randomly distributed over the workpiece surface. So, basically what we have seen in case of the built up chips, that the built up edge is formed on the tip of the tool with the material that is coming from the workpiece. So, some of the workpiece material will get deposited on the tip of the tool to form a built up edge, and it will be a gradual process and the material will be developed layer wise. It will grow up to a certain level, then it will become unstable and later on it will break up. So, when it breaks up, some part of the built up edge will be taken by the tool face of the chip and some part will be deposited randomly on the work surface. Now, the process of built up edge formation and destruction is continuous. So, once a built up edge will form, the tool is continuously performing the machining operation, it will eventually become unstable and then it will break. Some part will be removed with the chip, some will be deposited on the workpiece. Again, after some time the built up edge formation will start, then some part will be taken, and when it breaks, some part will be taken with the chip, some will be deposited on the workpiece. So, this will be a continuous operation. So, after some time it will form and it will break, then form, then break, form, break. So, this will be a continuous process. Now, built up edge affects the surface finish of the machined surface as it alters the geometry of the cutting edge. Now, the surface finish of the workpiece or the job that we are machining is affected by the formation of the built up edge. As we will see in our discussion regarding the geometry of a single point or a multi-point cutting tool, we will see that the tool is always given certain standard angles. It can be back rack angle, it can be side rack angle, end cutting edge angle, side cutting. So, different angles will be given to the tool point so that it performs the cutting operations satisfactorily. relief will be provided so that it should not rub against the workpiece. But when according to our specified geometry there is certain mechanism that is happening during the cutting operation, so that some material from the workpiece is getting deposited on the tip of the tool, then the geometry that we have designed for that particular operations will be altered. We have designed, suppose the back rack angle should be x level. After the formation of this built up edge, that x may change to x plus 2 or it may reduce to x minus 2. So, depending upon the built up edge formation, the geometry of the tool that we have designed will be altered, and if the geometry of the tool is not according to our design, is not according to our specifications, then the quality of the surface will get deteriorated, or the final product that we are going to get will not be according to the desired specification levels. So, the built up edge affects the surface finish of the machined surface as it alters the geometry of the cutting edge. So, that we have already seen, there is a standard geometry. If this formation takes place, the geometry will get changed. Then the work hardening and deposition of the successive layers increases the hardness of the built up edge significantly. Now, the work hardening is also taking place because the operation is also taking place at a elevated temperature. Some form of work hardening may take place, and the deposition of successive layers. We have seen that this built up edge will be formed successively, it is a gradual process, and in that gradual process number of layers will be deposited. Thus, the hardness of built up edge will improve or will increase significantly. Now, as we have seen, the built up edge alters the geometry of the tool and may result in rubbing action or may affect the surface finish of the final product. But built up edge therefore is generally undesirable, but a thin stable built up edge means a thin, it should not be very thick, and a stable, it should not be unstable, it should be stable. We have seen that after some time it will become unstable and it will eventually break, and some part will be carried away by the chip, some part will be deposited on the workpiece surface randomly. But if it is a thin built up edge and it is according to the geometry of the tool, or it conforms to the geometry of the tool. So, if it is thin and it is stable and it is conforming to the geometry of the tool, built up edge usually is sometimes becomes desirable because it reduces the tool wear by protecting the rack face of the tool. So, if the formation is taking place in such a way, in such a manner that the exact geometry of the tool that we have designed is not getting affected. First point, the built up edge is not very thick. Second point, and the built up edge is a stable built up edge. Then if these three conditions are satisfied, then sometimes the built up edge is desirable. Why it is desirable? Because it protects the rack face of the tool against wear. So, the excessive wear of the tool point geometry will not take place. This built up edge will cut the workpiece, and the surface finish that we will get under these limiting conditions will also be comparable, or it also will also be good. Now, the size of the built up edge is inversely proportional to the cutting speed. So, inversely proportional means that if built up edge the size is very large, it will result because of the slow cutting speed. If the cutting speed is very large, then the built up edge size will be less. Now, the size of the built up edge is inversely proportional to the cutting speed. So, speed more, size less, speed less, size more. Now, the built up edge formation can be reduced by, already in our discussion we have seen that usually or generally speaking built up edge formation is not desirable, but under certain limiting conditions it avoids the excessive tool wear by forming a gradual thin layer on top of the tool tip. But if we leave apart all those limiting conditions, we want that no built up edge formation should take place. So, how can we reduce the formation of a built up edge? So, the built up edge formation can be reduced by decreasing the depth of cut. So, the depth of cut that we give while the machining operation should not be too high. So, if at a particular level or a particular level of the depth of cut built up edge formation is taking place, then we do not want the formation to take place, we should decrease the depth of cut. Then increasing the rack angle. So, at higher rack angles the built up edge formation can be reduced. Then using a sharp tool. Sometimes if we are using a blunt tool, the chances of formation of built up edge are more. So, it is desirable that we use a very sharp tool, so that the built up edge formation is avoided. Then using an effective cutting fluid. So, if we are using a cutting fluid, there are every chances that the built up edge may not take place or the may not form. Moreover, it can be reduced. The chances of formation of built up edge can be reduced by using an effective cutting fluid. So, another important point to note is the higher the affinity of the tool and the workpiece material. So, we are using a particular tool, then there is a particular workpiece, the tool is going to go and machine the workpiece. So, these two are made up of different materials. If these two materials have very strong affinity among each other, then there are greater tendencies for the formation of the built up edge. So, the higher the affinity of the tool and the workpiece materials, the greater the tendency for built up edge formation. Now, it depends. If the affinity is too high, then there are every chances that built up edge formation is bound or is going to take place. Then the third category of chips are the serrated chips. So, serrated chips, also called segmented or non-homogeneous chips, are semi-continuous chips. So, these are in between the continuous and the discontinuous chips with zones of low and high shear strains. So, if we see the chips, there will be zone of high and low shear strains. Now, which type of metals will result into serrated chips? So, metals with low thermal conductivity and strength that decreases sharply with temperature. So, with increase in temperature, if the strength is decreasing, such as one example has been given, for example titanium, this type of behavior is observed, the chip have a sawtooth like appearance. So, even the appearance or the shape of the chip has been given, it will be sawtooth like. So, metals with low thermal conductivity and strength that decreases sharply with temperature, such as titanium, exhibit this behavior. The chips have sawtooth like appearance. So, serrated chips will be formed in between the continuous and the discontinuous chips, and these are particularly relevant when we are machining certain particular category of materials. What are the properties of the materials, which has already been mentioned here. Now, we come on to another category of chips or another types of chips, those are the discontinuous chips. So, discontinuous chips usually form under the following conditions. So, there are conditions for the formation of continuous chips, there are certain conditions for the formation of built up edge, there are certain conditions for the formation of serrated or segmental chips. Similarly, there are certain conditions. So, these conditions can be in terms of operating variables, these conditions can be in terms of the material of the workpiece or the tool material or any other parameter, for example the cutting fluid. So, discontinuous chips will also form under a particular set of conditions. So, what are those conditions? So, these conditions are the brittle workpiece materials. So, if the material is brittle, then there is every chance that the formation of chips will be a discontinuous chip. Then another important case is the materials that contain hard inclusions and impurities. So, while the initial stage, in the initial stage when the material has been formed, maybe it has been formed by casting operation. So, this cast product, if it has too many inclusions and impurities, there are chances that when we machine this particular cast product, we are going to get the discontinuous type of chips. Then if the very low or very high cutting speeds are used, at very low cutting speeds also we are going to get discontinuous chips, and at very high cutting speeds also we are going to get discontinuous chips. Then if the depth of cut is also very large, we are going to get discontinuous chips. Moreover, rack angles if are less will result in the discontinuous chips. So there are certain parameters, like if the material is brittle, rack angle is less, depth of cut is also large, then if the cutting speed is very large or if it is very small, we are going to get discontinuous type of chips. Then other parameters or other factors that result into the discontinuous chips are lack of an effective cutting fluid. If we are not using a cutting fluid, we are going to get discontinuous chips. Then low stiffness of the machine tool. So stiffness point we are going to address in detail. So if there is a lack of an effective cutting fluid, discontinuous chips will be formed, and if the stiffness of the machine tool is less, we are going to get discontinuous chips. So the forces vary because of the discontinuous nature of the chip formation. When the discontinuous nature of chip formation or the discontinuous chips are forming, the tool is not in direct contact with the workpiece. So the forces may vary. The rigidity of the tool holder, first point, work holding device, second point, and the machine tool is important. So the rigidity of the tool holder as well as the work holding device as well as of the machine tool thus becomes important. Otherwise vibration and chatter may be noted, adversely affecting the surface finish and the cutting tool. So when discontinuous chips are forming, the forces vary. There is a variation in the forces, and this variation may result in the excessive chatter or it may result in the excessive tool wear. But this can be controlled if we have proper rigidity in our tool holder. Even the work holding device is rigid and the machine tool that we are using is also rigid. Just to summarize, the forces vary because of the discontinuous nature of the chip formation. The rigidity of the tool holder, work holding device and the machine tool is important. Otherwise vibration and chatter may be noted, adversely affecting the surface finish and the cutting tool. So it will result in excessive tool wear and it will result in the surface finish deterioration. Now we have seen that there are different types of chips that are formed while we machine a particular material. So depending upon the type of the material, depending upon the operating variables, depending upon the number of other parameters, we will get different types of chips. So we have observed that with continuous type of chips there are certain problems. So we can see now we are going to address the aspect of chip breakers. So problem areas with continuous chips when working with automated machine tools. So when the automatic operation of machining is taking place and we are getting continuous chips, these chips may get entangled with the tool holder, these may get entangled with the workpiece or the waste disposal system. So this entangling may result into a number of failures, and if it is an automatic process, then we have to stop the process in between. Again we have to start the process, so there will be a break in the process. In order to overcome this kind of problem, in order to avoid the formation of continuous chips, we use chip breakers, which are nothing but it is a piece of metal that is attached to the tool. So problem areas are there when continuous chips are formed, and these problem areas are particularly relevant when we are having an automatic machining or automated machine tools. When all the independent machining variables are under control, when all the other variables are under control, speed, feed, depth of cut and all these parameters are under control, the procedure employed to avoid continuous chips is to break the chips intermittently using a chip breaker. So the procedure employed to avoid continuous chip is that we can break the chips intermittently using a chip breaker. The chip breaker is nothing, as I have already told, it is a piece of metal that is attached to the rack face of the tool. Now, most cutting tools and inserts are equipped with built-in chip breakers. So, initially we used to apply a piece of metal at the rack face of the tool, but presently most cutting tools and inserts are equipped with the built-in chip breakers. Now, chip breakers increase the effective rack angle of the tool and consequently increase the shear angle. So, this is what we will discuss when we study the mechanisms or the mechanics of cutting. The chips can also be broken by changing the tool geometry, thereby controlling the chip flow as in the turning operation. So, chips can also be broken while by modifying the tool geometry. So, tool geometry can also be modified so that the chip breaks when it slides over the rack face of the tool. Moreover, in case of interrupted cutting operations, what are these interrupted cutting operations? These interrupted cutting operations are, for example, milling. So, in interrupted cutting operations such as milling, chip breakers are generally not necessary. We are not requiring the chip breakers, since the chips already have finite length. The chips that are formed in milling operation have finite lengths because of the intermittent nature of the operation. So, the operation is not a continuous operation, it is an intermittent type of operation. So, while we use milling operation, we need not provide a chip breaker. So, we have seen that if continuous chips are forming, there are certain problem areas with the formation of continuous chips, and these, if all other independent variables, means we have controlled all the other parameters which can be controlled like speed, feed, depth of cut, and maybe other parameter like use of cutting fluid. Whatever all parameters that influence the formation of the chips have been controlled, then we can go for another important technique, that is we can break the chips using the chip breaker. So, with this we come to the end of this lecture on machining. We have discussed in today's lecture the basic fundamental principles of chip formation. We have seen what are the different types of chips are formed, what are the various conditions under which different types of chips will be formed, and later on we concluded that if all the parameters are controlled, even then we can break the chips using the concept of chip breakers, which are provided with the designs of the tools or the inserts, so that the chip curls over the chip breaker and breaks. In the subsequent lectures, we will discuss the other details regarding the machining operations. Thank you.
Thank you.